if R dq by dt plus Q divided by C is equal to V, then show that Q is equal to CV 1 minus e to the power of negative R or negative T over RC, given that Q is equal to 0 when T is equal to 0. Okay, now this here is the charge on a capacitor. Now, if we look at, first of all, let me just write what these mean. What you have is R is the resistance of a resistor. Of course, that would be in ohms. Q is the charge in coulombs. V is the EMF in volts. T is time in seconds. Okay, so and of course E is the Euler, right? As you know, 2.718 to 3 decimal places. Now, this really is the formula that governs an RC circuit: resistor, capacitor circuit. Alright? That's the formula that governs it. Now, when you connect a source, let's connect a DC source to it, the capacitor charges up. Right? And of course, if you disconnect the DC source and short circuit the source, the capacitor will discharge. Now let's put back the DC source there. So this is the resistor R and the capacitor C. Alright? Now, here, this is V. Let's rewrite this formula. R dq by dt. V is equal to R dq by dt plus Q divided by C. Now, here, voltage is the current time resistance. V is equal to IR. But at the same time, the current is the rate of flow of charges. Now this being the rate of flow of charges, it is the rate at which charge flows with respect to time. So it is dq by dt. Alright? So therefore, the voltage here is equal to the resistance times I, which is the resistance times dq by dt. So that's this part. Alright? Now, how about this part here? Now, the charge on a capacitor is equal to the capacitance times the voltage that appears across the capacitor. Alright? So transposing If we divide both sides, let me rewrite it like this: CV is equal to Q. Dividing both sides by C, we have the voltage is equal to the charge divided by the capacitance. So that's this part. So this is the voltage drop across the capacitor. This one is the total voltage applied. V is the applied voltage, or the voltage drop across the entire circuit, is equal to the voltage drop across the resistor, or the resistor, right, which is IR, and here this is the voltage drop across the capacitor. Now let's look at the formula. Let's rewrite it again. V is equal to R dq by dt plus Q over C. So V is equal to R dq, dq by dt plus R divided by C. Now, okay, good. Now the thing is, let's rewrite it as it was given originally, as it was presented, is equal to V. Or Q over C. Why am I saying R over C? It's Q over C. My. This is Q divided by C. Now when you look at this, you see that it is a differential equation. And you might remember that if you have dy by dx plus py equal q, this is a general form of a differential equation that can be solved using the integrating factor. So this takes a similar form as this, right? So let's see how this goes. We're going to, what we're really going to do is solve for Q using the integrating factor method. All right, we need to divide both sides by R so that we have the dq by dt, just like how you have dy by dx plus py equal q. So we can identify each part. Now here, all right. Now here we divide by R. So dq by dt plus q over rc is equal to v over r. Alright? Now let me rewrite this part like this: 1 over rc by q. So let's see if I can move the q here and put this as 1 divided by rc. Alright, so there we go with that. Now as you see here, instead of dy by dx, we have dq by dt. So q takes the place of y, t takes the place of x. Now, in this case, our p would be equal to 1 over rc. See that? That would be like our p. And our q would be, oh, I'm using q here twice because q already represents the charge on the capacitor. Alright, let me write this q like this, as if it's uppercase q is equal to v over r. Okay, so that's what we have. What is the integrating factor in here? Remember, when we had the formula like this, the integrating factor would be e to the integral of p dx, right? For this one, it would be e to the integral of p dx. That would be the integrating factor. Now, our p is 1 over rc. So, our integrating factor here is e to the integral of 1 over rc, not dx now, because remember, t is taking the place of x, so it is dt. That is our integrating factor here. So, here now, what does this turn out to be? Our integrating factor here is e to the, now when you integrate here, remember 1 over rc is a constant, right? When you integrate a constant to the, with respect to x, to d, it's like you're saying integral of 5 dx. This would be what? It's like 5 times the integral of 1 dx. So it would be like 5 times the integral of x to the 0 dx. Just to recall here, so that's 5 x to the 0 plus 1 over 0 plus 1, which is 5x to the 1 over 1, which is just 5x. So you integrate a constant with respect to x, you get the constant times x. So here you integrate a constant with respect to t, you get the constant times t. Alright? So this happens to be e to the t over rc. You see that? That's our integrating factor. Now the next thing we do, you remember, multiply by the integrating factor. We're going to multiply both sides of the equation by the integrating factor. Now, what we have then is the integrating factor, in this case e to the t over rc multiplied by dq by dt plus e to the t over rc multiplied by 1 over rc times q is equal to e to the t over rc multiplied by v over r. Okay, and by the way, if you look back at this, you see it's a current, right? Rate of change of charge with time plus Q over RC equal V over R. I equal V over R. Alright. Now, let's look at what we have here. Right? Now, remember that what we have here is the result of having performed a differentiation using the product rule. Right? So what we're going to do is apply the reverse product rule. Now, remember what the product rule says, that if you have two functions, right, u times v, when you differentiate the u times v, you hold u and find the derivative of v, plus you hold v as it is, times find the derivative of u. Alright, so the derivative of the product of two functions of x. To find it, you hold one product as it is, multiply by the derivative of the other product, plus the product you just differentiate, you hold it as it is, times the derivative of the other product that you held before. So this is the product rule. You remember that. Now, we have the result of having applied a product rule. So what could it have been that you differentiated? What could have been the product here? Now, look at this. Consider that you differentiate Q with respect to time. If you find the derivative of Q with respect to time, you would get dq by dt. So, one of the items that you would have multiplied would have been q. Right? You differentiate q. Now, it means that you would have held e to the rc. So you have e to the t over rc. So you have e to the t over rc here. Now, if that is the case, it means in the other part of the equation, you would have differentiated e to the t over rc and hold q, and that's what you see happen here. Right? Now, by the way, let me just put the 1 over e to the t over rc in front to follow the usual method. When you differentiate e to the t over rc, it's like you're differentiating 1 over rc by t. Let's write that. It's 1 over rc by t. Now, if you remember, when you have y is equal to e to the ax, and if you mentally remember your differentiation by substitution or the chain rule, you see that dy by dx would be a e to the ax. You remember that? Now this would be like your a, so it's a similar thing. So you multiply with the constant, 1 over rc comes in front, just like the a comes here, times e to the 1 over rc by t. It's like you have e to the a x. Alright? So that's what you have there. So it means that this was differentiated. Alright? With respect to t. So here now, you say that there would be equal to e to the t, that would be equal to e to the t over rc multiplied by v over r. Alright, so that is what you have there. Now what's the next thing you do? You run out of scrolling space, you know. Alright, we have a little more space under here to take the next step. The next thing that you do is to integrate. So of course I wouldn't have to tell you it's both sides, because when it comes to an equation, anything you do to one side you must do it to the next side as well. Alright, so what you do is integrate both sides. Now you find the integral of e to the t over rc by q, and you're integrating with respect to t, is equal to the integral of e to the t over rc and v over r dt with respect to t, right? Alright, so let us draw a line and continue working on the other side of the line, because we have run out of scrolling space. We can't scroll down anymore, right? Alright, so it was the integral of e to the t over rc. What we have is the integral of e to the t over rc multiplied by what again? Let's scroll back down. D multiplied by q dt. Alright. So integral of that integral, just to make sure, of q dt over rc multiplied by q dt. Oh, hold on, I left out a little thing here. One thing I realized I left out. I had said we looking at the inverse product rule, the reverse product rule. That means there is something that we differentiated in order to get this. What we differentiated in order to get this is this. So I should show that it is a derivative. It is really d by dt of this, right? I left that part out earlier. The derivative of this, the derivative with respect to t of e to the t over rcq gives this on the left hand side. When you differentiate this, you get this. You hold e to the t over rc, differentiate q with respect to t to get dq by dt, plus You hold Q as it is times differentiate e to the t over RC to get this. Alright? So you see that? So 1 over RC here. Alright, so this is what you get. So what you're integrating here is the derivative with respect to t of e to the t over RC by Q. You see that? Alright, so you're integrating d by dt of put Q e to the t over RC. Alright, let's write it like that. So you're finding the integral of Q times e to the t over RC. What else was there? Q e to the t over dt equal the integral of. So dt, showing that t is the variable. This is equal to the integral of, what was it again? e to the v over r times e to the t over RC dt. So it is v over r times e to the t over RC dt. Just I put the constant on the left and then the function on the right, because q is a constant, v over r is a constant, right? Well, q is a function. It's a function, it's a charge. It's two functions here that the two functions that we integrating. Two functions of t, q and e to the t over RC. That's why we got that product rule earlier. But here, v over r is a constant. Alright? So, that's what we have. Now, here, the thing is, you notice what I did again. I left off the d by dt. It should be between the integral and the e to the t over RC. I left that off again. It is the derivative with respect to t of. Alright, so let's just double check, make sure everything is alright. The integral of d by dt of q e to the t over RC dt. The integral of d by dt of q e to the t over RC dt is equal to integral of e to the t over RC. Well, integral of v over r e to the t over RC dt. Integral of v over r e to the t over RC dt. Nice. Now, you are integrating a derivative. It's like the integral and derivative cancel out each other. Just like square and square root, multiplication and division, and so on. Right? When you integrate the derivative of a function, the function is left undisturbed. So what you have left is q e to the t over RC. And then what is that equal to? Right? What's that equal to? No. Let's rewrite this part on the right. But guess what? You see, since v over r is a constant, we can write it outside of the integral sign. It makes the integration less messy. right? You don't have to worry about that constant being there. So we're integrating e to the t over rc with respect to t. All right. So q equal q. Let me just use one color now. E to the t over rc equals v over r times. Remember, when you integrate a constant times t, what we're going to get is this. It's similar to saying y, or let's not bother with the y. The integral of e to the ax dx, right? Integrating by substitution, you're going to get e to the ax divided by a, the constant a. Remember that, alright? If you don't remember, let me know so that I can link a video to it or to show this again. So here, this is like, let me rewrite it in another way, 1 over rt or 1 over rc by t. I could rewrite this as 1 over rc by t dt. So this part is a constant times t, right? So what you have is e to the 1 over rc times t divided by 1 over rc. You divide by the constant, and then plus your constant of integration. All right. C is already being used to represent capacitance, so let's use K for our constant then. We don't want to mix up the two C's, right? So that's what we have. Now, let me see. Let's rewrite this part here. So what we have is q e to the t over rc equals, remember when you have something divided by a fraction, it's the same as that thing multiplied by the reciprocal of the fraction. So if we have v over r, and this is divided by 1 over rc, is the same as multiplying by rc over 1, right? E to the, I could rewrite this as just t over rc. I separated the t from the 1 over rc to show the constant clearly before, plus k. Oh, look at this. Resistance will cancel resistance. So what we have is q e to the t over rc equals v times c, right? It's v, put them alphabetical order, c times v, cv e to the t over rc plus our constant of integration, right? Now we want q, so let's transpose for q. Let's divide by e to the t over rc. So we have q equals, the e to the t over rc would cancel itself on the left. On the right you have cv e to the t over rc divided by e to the t over rc plus k over e to the t over rc, right? You see that? But here e to the t over rc cancels itself. So you have q is equal to cv plus, alright, you see, let's recall one of our laws of indices, right? When you have something over a number raised to a power, it's the same as that thing multiplied by the number raised to the negative of that power. Alright? So this would be like K e to the negative t over RC. See that? Now, we want to find out what K is, what the constant of integration is. Remember, initially, they say Q is 0 when T is 0. So, initial conditions, Q is 0. So, we can use that to find out what K is equal to. So, Q is 0, 0 equals CV plus K e to the T is 0. So, it's negative 0 over RC. But 0 over RC is 0. So, it's negative 0, same as positive 0. But when you raise a number to the power of 0, you get 1. Okay. So, from this, if you can see, if you subtract CV from both sides, and you say negative CV equal K. So K is equal to negative CV. Alright. So that is what we have. Now, in that case, we can rewrite the formula. Now here, we have this times this. Oh my, wait, hold on. The V over R. Oh yeah, I have the V over R here cancelled, so we get CVE to the, okay, yeah. One thing I left out, remember the V over R multiplies everything. So I left out the bracket. I should have put a bracket around this. Right? When you don't put a bracket, you tend to forget that the V over R should be multiplying everything. So when we remove a bracket, the V over R multiplies the e to the 1 over RC t over 1 over RC, right? So it takes care of this part. So you multiply the V by the RC, as we saw earlier, times e to the 1 over RC. But you must multiply this too. The V over R must multiply the K. Right? Mistakenly left that out. The V over R multiplies K. So K, the V over R multiplies the entire integral. So it multiplies the function and it multiplies the constant of integration. Right? So I left that out earlier. V over R times K should be K V over R. V over R. Right. So that's what I should have. So this is V over R. Alright. Oh, so K would no longer just be CV, you know. Guess what? What you would have is negative CV is equal to V over R K. Right. So you transpose for K. If you multiply both sides by R, you get negative CV R equal K. Equal V times K, and then you divide by V, you get negative CVR over V equals K. So therefore K equals, well, R would cancel R. So R, you have negative CVR, and then you divide by V, not R, my. You have VK, so you divide by V, not R. Oh boy. You divide by V, right? So V cancel V, what would you have? Negative RC then. K would be negative RC. So that's what you would have. Right. Okay, so it looks alright now. So in this case, this being the case, right, you have, when you rewrite everything up here, you would have Q equals CV plus V over R times K, right? So you have V over R times K. But you have to consider what is K. K is negative RC. So it's V over R multiplied by negative RC. Alright, it's not bad. Put the bracket. V over R multiplied by negative RC times e to the negative t over RC. Right. Oh, but guess what? R cancels R here, you know. Right? R would cancel R there. So what would you have there now? Q is equal to CV. You have a minus sign here, so might as well just put minus. Minus the C and the V remain. So you have a C and a V here. E to the negative T over RC. And then you factor out CV, so you have Q is equal to CV, open bracket, 1 minus e to the negative t over RC. Okay, so is that what we had before? That you should show Q equals CV, 1 minus e to the negative t over RC. Right, good. So here you can write shown. Alright. So that will be it for now.